This is the title of my talk, The Understanding of Phase Transition Through Mathematics, a quantum version of the Youngly theorem and research hero. This is my name and affiliation. Acknowledgement is the RRI library and ICTS library, particularly this Ramon Research Institute, how they help me since 21 to 22 years. If they stop my help, my research will be reduced by 1/3. Okay. And then the CRG project, ACR with Government of India, and also Emory University Press has noticed a couple of my work, and also they are helping me. And I am lucky that Dr. Ijoy Pathak is my postdoc, such an intelligent student. If you don't discuss him on the board, you will not able to understand his level of intelligence. I am understanding his level of intelligence. Now the thing is this outline of the talk. What is the Youngly theorem? How the imaginary magnetic field appears in the real world? What is research zero? A few result of our, honestly speaking, we are also in the learning stage. We got some interesting result and also formulated the furthermore problem. Still the many calculation has not completed. Whatever we have done this calculation here, it is as exact as possible. Okay. And then this my personal eating with Professor C.N. Young, I will tell you explicitly detail, and then the conclusion. The main motivation, the main objective of the study I'm going to present here, how to retrieve the result of Marmin, Wigner, and Hoth theorem from this Youngly theorem. Explicit calculation I will show to you. And the topological aspect of the Youngly zero theorem, how to construct the quantum critical lines from the Youngly zero theorem. I will show you one-to-one correspondence with all exact calculations. And the Youngly circle theorem is always circle, just to raise the question and show you explicit detail. Okay. Now the question is, when I start this subject, this is the original paper, the subject has started by Professor C.N. Yang and Lee. It was very hard to understand me. But when I read these two books, I particularly his book has helped me a lot to understand this subject. A few basic aspects of statistical physics and the Youngly theorem. Birth of the statistical mechanics provided as the mechanical expression of many thermodynamical phenomena. It established a relation from the microscopic to macroscopic world. It is the primary importance of the physics, and all of you know in the year 1924, Ising itself in his thesis showed that in one-dimensional case undergoes no phase transition at t equal to 0. He has done most probably the transfer matrix method. Also in this lecture, I would like to see through the Youngly theorem also. Okay. And then the Onsager showed the square lattice Ising ferromagnet undergoes a phase transition at a critical temperature when no magnetic field is applied. I have heard that nowadays the two-dimensional Ising model in a non-zero magnetic field is remain unsolved, but I don't know it yet. The very basic aspects, a few basic aspects of the Youngly model, I have already shown you side-by-side new paper with regarding the partition function as some external field. I would like to show you explicit detailed calculation whose domain can be extended in the complex plane. In particularly, this theory provides a series of Youngly theorem and how the imaginary magnetic field come. Okay. This is the thing. When I first read that paper, I'm thinking it is real world. And where is the imaginary magnetic field is coming? This is the case. And then I will show you the experiment also. Let the singularity of energy, h of the zero, the partition function in a complex field, often termed as the Youngly zero. Kindly say, partition function z is usually positive as it is a sum of exponent, but can vanish if we consider the complex values of field. The vanishing of this partition function is directly related with the free energy. Can we realize from the fact that the logarithmic function is singular only at the origin? The Youngly theory rigorously justifies this intuition and provides a unique point of view of force transition Ising order problem as such a gas problem. The imaginary magnetic field in the real world. Okay, then when the T is then EC, the system is in the ferromagnetic phase or any ordered phase. The circle imaginary real is the closed circle. But here in this case issue, the circle is not the closed circle. And this is the experiment in the ERL paper 2015 and also 2017. That is, this experimentalist has found the evidence of it. And one can also find this Youngly singularity in the fugacity plane or in the magnetic plane. And this is the classical physics of this temperature. I would like to do the same thing that I have told, that is the paramagnetic to ferromagnetic, but mind it, it's a 2D case, not in the 1D. Now I prove this Marmin-Wigner-Roth theorem or in this Ising, what you call the thesis. Simply, I take a ferromagnetic chain. The transfer matrix I can write in that way. So the partition function also I can write away. The sum is the eigenvalue that I can gain. So the total sum Zn equal to in this case. So the Youngly zero, that is the partition function zero, implies this condition with this condition. And also after some, it will be very easy mathematics, I can also see in that way. Here, kindly see, Hn we define the magnetic field along imaginary direction I theta n. Theta n is the mathematical. Here, K is absorbed at a finite temperature. So the magnetic field can exist in the zero and come to the EL axis when pins the transition if the theta n equal to 0, means the cos theta n equal to 1. By this factor and this factor, the cos theta n ever became the 1. We just derive the well-known result, that is, there is no transition in 1D for finite temperature. Marmin-Wigner-Roth theorem, and also at the same time, you can see the 1924, that is this Ising thesis. Now I go to the other point, the starting Hamiltonian. If you see the first term and third term, this is nothing but the quantum Ising model. And this is the three-side interaction term. I can do after the Jordan-Wigner transformation this case. And this is the completely quantum phase diagram of our ordeal Hamiltonian system, 3 quantum critical line, and it's a special line marked by this. Sometimes the people not even go to the literature. And this is the detailed mathematical derivation of this quantum critical point, critical point, and the quantum critical line. I have 2-3 minutes, no? Okay. Now the thing is this, now I come to the detailed quantum version of the Youngly zero. If you notice that this model is a very beautiful model. If gamma equal to 0, xy model with a transverse field, if gamma not equal to 0, and an anisotropic xy model in a transverse field, if gamma equal to 1, this is nothing but this quantumizing model. So let's see. If I do the partition function in that way, the zeros of the partition function, sometimes historically called Youngly zero theorem, I can write it. Here n is the Artsubara frequency, T equal to temperature. And I write my magnetic field in terms of way. You see that it's a EL part and it's an imaginary part. So I get the 2 component. When T equal to 0, that I'm doing the quantum version of it. Let's go to this, and also this is the trajectory of it. For gamma equal to 1, for the quantumizing model, it became the circular. So this is the Youngly circle theorem also in my mathematics. Okay, now I do the detailed mathematics, detailed derivation of it, a detailed derivation of the quantum version of Youngly theorem. If you see, here is the transverse field or magnetic field in my field, 2 components. And then 2 components here, alpha T equal to 0, this imaginary part should be 0 when the transition occurs. I got this from this calculation, and I get at the end of the day 1-to-1 correspondence with the quantum critical line. This calculation as exact as possible, and the Fisher zero imaginary time derivation is this formula. If you see from this formula, I have derived it from the left-hand side to right-hand side equality. So now at first step isn't when alpha to lambda 2 equal to 0, quantumizing chain, and you see -1 to +1, and if I only plot -1 to +1, it's a circular rectangle. And also if this is t equal to 0, but if I introduce the finite temperature, depending on the values of temperature, we have find the gap. There is no transition. That is, the circle is not closing. Okay, now I get to the lambda 2 term. When the three-side interaction term, the third of my criteria was there. Are the circular theorem, Youngly circular theorem, are always circular? No. I would like to come to this point again. So if you see here, this criteria, if you see this point, this point, this point touching the real axis, means the imaginary components at the 0. Also here the 0. Some points very closely circular, but not the whole. You see here, this is elongating. And also the thing is this point are all nothing but the quantum critical point touching when we have done it. Okay, at the same time we have done for a finite temperature, we are finding the gap. Okay, now the question is Fisher zero I have done. In the Fisher zero, when I done, you see that k equal to 0, lambda equal to u, lambda equal to mu, this transition occur. It is the maximum. It is the imaginary temperature. Imaginary magnetic field, Fisher zero, imaginary temperature. I can also do the beta, I can write beta r plus I beta I. Sir, honestly speaking, that mathematical calculation, we got some result, but still we are not happy with this. So I am not presenting here. I am only presenting the only one part of it, okay? Now, the thing is this, I would like to go to the quantumizing chain for the longer range or the E-type chain. You see, here, the lambda 2 equal to minus mu, the quantum critical line. That you see here, cos inverse minus lambda 1, lambda 2, for these values of k, this is the highest peak of transition, and this is the imaginary temperature we are getting here, okay? Now the question is, here we are showing same behavior, but not the peak, that is not a high temperature. So I told lambda 2 equal to beta plus lambda 1. The other critical line, here the quantum critical point here at the k equal to pi, you will see at the pi that transition. And this is the quantum critical line conditions satisfied, and those were away from that, and so the divergent value is slowly, gradually decreasing.
Is it okay to wrap it up?
Okay, yes, just only 1 minute, and this is the lambda 2 equal to lambda 1 minus 1. Same thing we kept found it in detail for the other critical line. My personal meeting, I meet Professor Sienian, 2013 December to 2014 December, side by side office with a common partition wall. He has studied his degrees in university, also same university name in the Taiwan science. I was in Taiwan science in the NCTS, National Center for Theoretical Science, and Professor Sienian has told to publican and also to me that his first lovable subject is the H-field theory, from which he got the Nobel Prize, and second is loving this Youngly theorem. He sees the whole of transition in terms of mathematical physics, and that mathematical physics 1952, to the best of my knowledge, sir, I am trying to best to borrow it today from this classical physics to the quantum part. Okay, now the thing is this conclusion. We have presented a few basic aspects of Youngly theorem. We have started also presented the result of Youngly zero from the perspective of the quantum version. We have interpreted the Marmin-Wigner-Ho theorem from the perspective of the Youngly theorem. We have presented the study of Fisher zero. Is that my other? Okay, any questions and comments?
Any questions? Okay.
Or any of you know my mail ID. If you have any personally to contact with you, send the mail. I give the answer of your all questions. Okay, and also I'd like to thank all of you again that you give me an opportunity to come here again. Okay, thank you.
Let's thank Sujit again.